Okay, folks, we're back with the second reading on quantitative methods, probability concepts. This one's twice as exciting as reading number 7. So here we go. You're going to love this. Some basic terminology to begin with. First is a random variable. This is an uncertain number. This is the variable to which we're going to assign a value when we perform whatever our random experiment is. So maybe our experiment is going to be rolling a die, and the random outcome would be what number comes up on the die. So the random variable is what number comes up on the die. Until we roll the die, we don't know what it's going to be. After we roll the die, it's a 1, or it's a 2, or it's a 3, or a 4, or a 5, or a 6. That's the outcome. That's the value of the random variable when we do our experiment. An event is a set of one or more outcomes. So rolling a die, getting a 1 would be an event. Getting a 3 would be an event. Getting an odd number, that's 3 possible outcomes, 1 or 3 or 5. That would be an event. Getting a number greater than 2, that would be a 3, 4, 5, or 6. That would be an event. Any one or more possible outcomes put together, we call that an event. We have 2 terms that we use to describe events. The first one is mutually exclusive. We have 2 events. If we say they're mutually exclusive, that means that they cannot happen together. Think of tossing a coin. Getting heads, getting tails, they're mutually exclusive. If you get heads, you can't get tails, at least not on that toss. If you get tails, you can't get heads. So knowing that you got one tells you you can't get the other one. That's mutually exclusive. Under exhaustive, I want you to add an extra word. So here, in front of exhaustive, I want you to put in an extra word here. It's an adverb, collectively. We say collectively exhaustive. And that means that if you take all these events together, it covers all possible outcomes. Now, you have to be careful when you use the terms mutually exclusive and collectively exhaustive. Some people think that they're somewhat complementary or that they mean the same thing. Clearly, they don't mean the same thing. But remember that it's possible for events to be mutually exclusive and not exhaustive. For example, when you roll a die, getting a 6 and getting a 4, those 2 events are mutually exclusive, but they're not exhaustive. There are 4 other possibilities, a 1, a 2, a 3, and a 5. And if they're exhaustive, it doesn't mean they're mutually exclusive. For example, getting all the numbers less than 5, 1, 2, 3, and 4, and getting all the numbers greater than 2, 3, 4, 5, and 6, those 2 are exhaustive, but they're not mutually exclusive. They have overlap right there in the middle. You can get a 3 or a 4. That would be in either of those 2 events. So please be careful when you think about the terms mutually exclusive and collectively exhaustive, that neither one of them necessarily implies the other one. Part of the reason that people get confused about this, as you will see in ensuing slides, is that frequently we use those terms together. We want to talk about events that are mutually exclusive and also collectively exhaustive. So make sure that you understand those 2 don't really have anything to do with each other. 2 different, it's like saying something is tall and saying something is wide. It can be both, it can be neither, but the terms don't necessarily have anything to do with each other. Okay, a couple of properties of probabilities. First of all, the probability of an event. Go back to the earlier slide, you know that an event is a combination of outcomes. Could be one outcome, could be more than one outcome. Whatever the event, the probability of that event is between 0 and 1 inclusive. It could be 0, it could be 1, it could be any number in between those 2. Now we come to exactly what I warned you about earlier. We have a set of events that has both of those characteristics I mentioned a moment ago. They are mutually exclusive. So any one event in our set means that if that one happens, none of the others happen. They're all mutually exclusive. And they're collectively exhaustive. We know at least one of them has to happen. And because they're mutually exclusive, we know that at most one of them happens. Another way of saying it, we have a set of events, exactly one of which has to happen. When that's the case, the sum of all the probabilities is 1. So, tossing a coin, heads, tails, mutually exclusive. If you get heads, you can't get tails. If you get tails, you can't get heads. And collectively exhaustive. You got to get one or the other. There's no third possibility. Then we know that the sum of the probability of getting heads and the probability of getting tails has to total 1. Now, it doesn't tell you what those two numbers are. Could be a 60% chance of heads, in which case it would have to be a 40% chance of tails. It could be a 55% chance of tails, in which case it has to be a 45% chance of heads. We don't know what either one of them is by itself, but we know that when we add the two together, it has to total 1. When we roll a die, we have 6 possible outcomes if our events are get a 1, or get a 2, or get a 3, a 4, a 5, a 6. If we have 6 events, those 6 events are mutually exclusive. If you get a 1, you can't get a 3, and so on. And they're collectively exhaustive. Whenever we roll the die, we know the outcome is going to be one of the ones on our list. The sum of the probabilities has to be 1. They don't have to be equal. We could have a 10% chance of getting a 1, 2, 3, 4, or 5, and then a 50% chance of getting a 6. Still adds up. That's perfectly fine. The sum has to equal 1. All right, some more adjectives to describe types of probability. I'm going to take the middle one first. So let's start off with subjective probability. Subjective, that's based on personal perception. That's your gut feeling. That's your guess. That's, what do you think might happen, but you don't really have a good reason for thinking it might happen. You don't have any data. This is just sort of how you feel today. And your subjective probability might be different from the subjective probability of the person sitting next to you, or the subjective probability of your best friend or your parents or whatever. This is, if you will, the squishiest of the three. It's the one that's based least on data and most just on personal feelings. All right. The second one I'll mention is empirical. This is based on an analysis of data. So whatever probability you're trying to investigate, you've already done some experiments and gotten some data. Maybe you want to know what the probability is of getting heads when you toss a particular coin. Well, you got the coin and you tossed it 1,000,000 times. And out of that 1,000,000 times, you got 600,000 heads and 400,000 tails. Your empirical probability of getting heads would be 60%. 600,000 divided by 1,000,000. It's based on an analysis of actual data. The final type of probability, a priori. This is based on reasoning, not experience. It's not based on analyzing data from the particular situation that you have at hand. For example, most people would say that the a priori probability of getting heads or tails, 50% heads, 50% tails. They base it on reasoning. They look at the coin, they say it has 2 faces, no reason to think that one of those should come up more often than the other, so it's 50-50. Now, a priori, that means before the fact, before we've done any experimentation, that probability might change once we start doing an experiment. We might initially say a 50-50 chance of heads, 50-50 chance of tails, but then as we start experimenting, we may change our estimate of what those probabilities are based on the information we get from our experiments. Calculating odds. This is an example that is very dear to my heart because I'm a horse owner. I love horses, so I love thinking about examples that include horses. So we have the probability that a horse will win a race as 20%. 20%, that's 1 out of 5. If this horse runs 5 races, we expect it to win 1 time, lose 4 times. It's probably not going to lose too bad. It's going to come in second or third, let's say. To calculate odds, we have odds for and we have odds against. You have to be able to calculate either one. The formula for odds for, sometimes it's written as odds for, sometimes they write the phrase odds in favor of. So do me a favor. Right here, above 4, do me a favor and write in another phrase, odds in favor of. Another way of saying it, odds in favor of, odds for. You take the probability of success, 20%, divide that by the probability of failure, 80%. 0.2 divided by 0.8, 1/4. We usually read this as 1 to 4, and it may be written, do me a favor, write another note over here, it may be written as 1:4. Usually when you see people discuss odds, that's the way that they write it. So be prepared, you may see it as 1 divided by 4 or 1:4. That's the odds in favor. The other thing you may be asked to calculate is the odds against the horse winning the race. It's exactly the opposite. It's the reciprocal of the first one. You take the probability of failure, 1 minus 0.2 or 0.8, and divide that by the odds of success, 0.2. That would give you 4 divided by 1. We would read that as 4 to 1. Again, we might see it written this way, 4:1. These represent the odds of a fair bet. And bear in mind that when you are talking about a fair bet odds are always the odds against this event happening. Make sure you understand that. So if our horse ran 5 races, we expect it to win 1 time and to lose 4 times. If it wins once and it pays us 4 to 1 on a $1 bet, that would be winnings of $4. If it loses 4 times, we would lose $1 each of those times. That would be $4 lost, $4 gained on the win. Our total is 0. Odds against represent what we call a fair bet. If we are accurate in our probability of the horse winning the race, then the odds against, if we get paid off at those odds, we should expect our winnings to be 0. Win some of the time, lose some of the time, net $0. A couple of other adjectives for our probabilities. Unconditional probability. This is probability when we don't have any information that may help us determine whether the likelihood of this has changed or not. It says that's the probability of an event regardless of the outcome of other events. For example, the probability that the market will be up for 1 day, not knowing anything else, not knowing that a number of businesses have exceeded their earnings expectations, or not knowing that the Fed has decided to lower interest rates, not knowing anything at all. What's the unconditional probability? Conditional probability is the probability of an event happening given that we know that some other event has happened. Now, it doesn't necessarily mean that knowing that that other event has happened will have any influence. Maybe it does, maybe it doesn't. But if we know this other event has happened, then we refer to it as conditional probability. By the way that you read this notation, that P and then a parenthesis, A with the vertical bar, B, the other parenthesis, the way that we read that is the probability of A given B. That's the probability that A happens given that we know B happens. The example probability that the market will be up for the day. That's the same as the A we had up above, given that the Fed raises interest rates. Well, knowing that the Fed raised interest rates probably will change our expectation of whether the market would be up or not. If you were rolling a die, let's say it's a fair die. So we got 6 faces. Each face has a probability of 1/6. If we roll the die and we have no other information and we wanted to know the probability of getting a 5, that probability is 1/6. Suppose we roll the die and a friend of ours looks at it and says, hey, that's an odd number. Well, given that it's an odd number, the probability that we got a 5 is now 1/3. There are only 3 odd numbers on a die, 1, 3, and 5. They're all equally likely. So once we have the information that the number's odd, that has changed the probability of getting a 5. By the way, if our friend had looked at it and said it's an even number, that also would change the probability of getting a 5. Getting a 5, given that it's an even number, that probability would be 0. Some rules of probability. The first is the addition rule. Now, once again, you have to understand the notation that we have here. The probability of A or B occurring, notice on the left we have the probability of A or B, and the way that you read that, that means A occurs, or B occurs, or both. If both of them occurs, that's okay too. This is not an exclusive or. It's not A occurs but B doesn't, B occurs but A doesn't. It could be A, or it could be B, or it could be both. That's equal to the probability of A plus the probability of B minus, and remember, you have to understand this notation here. When we write A, B together, that's the probability of A and B occurring together. This is the formula that you would use, and a few slides from now I'm going to show you a really nice picture that explains why this particular formula works. At the moment, I want you to take it at face value. This formula works. Wait a few slides and you'll see a nice cool picture that will explain why. For joint probability, probability that A and B both occur, notice we have the multiplication rule. The probability of A and B occurring is the probability of A given B times the probability of B. So think about this. Come up with a couple of example events. What is the probability that your lawn is wet and there's a rabbit out there? Whatever. You have a rabbit out on your front lawn. The lawn could be wet, the lawn could be dry. That would be the probability that the lawn is wet times the probability that the rabbit is out there given that the lawn is wet. I know it's a strange example. Maybe rabbits like your lawn more when it's wet. Maybe they drink the water off the grass. I don't know. We have rabbits out in our front yard. They're just annoying. Anyway, the point is that the probability of A and B is the probability of B, the unconditional probability of B, times the conditional probability of A given B. Now underneath that, I want you to write another rule very similar to this one, and that is that the probability of A and B is equal to the probability of B given A times the probability of A. So you can do it in either order. You can have the probability of A given B times the probability of B, or you can have the probability of B given A times the probability of A. These are the same. These are both equal to the probability of A and B. And somewhere off to the right, I want you to put another little note. Put this in parentheses. Write down Bayes. Oops. I hit the caps. Bayes formula. These two formulations put together are going to show us how we get Bayes formula in a few slides. So this is sort of a precursor to Bayes formula. It will help make Bayes formula a lot clearer once you get there. Okay, the last rule that we have here is the multiplication rule for independent probabilities. Now this doesn't make a whole lot of sense at the moment. I'll explain why it does. I want you to add a little bit of text down here. If A and B are independent, the probability of A given B equals the probability of A. Oops, I forgot a parenthesis. And the probability of B given A is the probability of B. So write that down, write that note under there. If A and B are independent, notice what it says, what I just wrote there. It says that if A and B are independent, then the probability of A given B is the same as the probability of A. That is, whether you know that B happened or not doesn't change anything. The probability on A stays the same. If you have a coin in your right hand and a die in your left hand, and you toss the coin and you get heads, and you roll the die, knowing that you got heads on the coin doesn't tell you anything about what number you're going to get on the die. They're independent. Similarly, whatever number you get on the die, if you roll the die and you get a 4, doesn't tell you when you toss the coin whether you're going to get heads or tails. So we say two events are independent when knowing that B happened doesn't change the probability of A. The conditional and unconditional probabilities are the same. Knowing that A happened doesn't change the probability of B. We don't. The two are independent. Neither one tells us anything about the other. Once you understand that idea, then it's very easy to understand this formula. Because this formula is simply the same as this formula up here. These two are the same with the probability of A given B equaling the probability of A. So take a look at those. You'll see that those are exactly the same if they're independent. That's really, really useful. And we'll use this a lot. For example, when you toss a coin multiple times, we assume that the probability of getting heads on the first toss is the same as heads on the second or the third or the fourth. Those probabilities are independent. If you know you got heads the first time, it doesn't tell you anything about whether you get heads the second time. We can use the multiplication rule then for figuring out whether we'll get several heads in a row, several tails in a row, and so on. Okay, some more probability rules. The total probability rule. Once again, you need to know some notation. So do me a favor. I want you to put a little box around, see this B with the superscript C, B with the little c up and to the right. That C means complement. B complement. The complement of B is not B. It's everything other than B. So let's say event B is rolling our die and getting a 6. Then the complement of B would be rolling our die and getting everything other than a 6, a 1, a 2, a 3, a 4, or a 5. That's what that notation means. Now the rule says that the probability of, we can chop the probability of A up into two pieces. We can chop it up into one piece where A occurs and so does B, And we can chop it up into another piece where A occurs but B does not. If you draw a picture, this is a whole lot easier to see. So I'm going to draw a little oval here, and this oval here, this is my A, and let me divide it up into a couple of pieces here. On the left we have A and B. And on the right, we have A and B. I can't write it as a superscript, so I'll write it as a subscript. A and B complement. And this whole thing, this whole green oval is my A. So we can chop A, or event A, we can chop it up into two pieces. A occurs and so does B, or A occurs but B does not. And therefore the probability of getting A, the size of that whole oval, is the size of the piece that has B in it plus the size of the piece that doesn't have B in it. Okay? Similarly, for the one below, we can chop A up into a whole bunch of little pieces, S1, S2, S3, all the way up to Sn. Let's see if I can draw a picture that'll give you an idea on that. Okay, now we got this sort of circly thing, and that's our A. And now I'm going to chop it up into a bunch of pieces. So there's 1 and 2 and 3 and 4 and 5. If I were a better artist, this would look prettier. Okay? And this piece is going to be S1. And this piece over here is going to be S2. And this piece over here is going to be S3, and so on. And so we can take the whole probability for A, the whole green oval there, and chop it up into A plus S1, this top triangle, or wedge, I guess, top wedge, and A plus S2 for the next wedge, and A for S3, and the next wedge, and so on. And what's important is that the probability of S1 plus the probability of S2 plus the probability of S3 equals 1. That is, I want you to write another note down here. S1, S2, dot, 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 Sn are mutually exclusive and collectively exhaustive. There you go. If that's the case, then we can chop up the probability of A into all these little pieces. Okay? If you can draw these pictures, then you will definitely get these rules correct. These are good pictures to draw. I would suggest that you take a look at those, you practice that a couple of times. And by the way, just as a general rule, when you are working problems like this, or when you're working cash flow problems and so on, there is nothing wrong on this exam with drawing pretty pictures. They give you some scratch paper. If you need to draw a timeline so that you can do a cash flow problem, or you need to draw some circles and some lines so you can do a probability problem, if that'll help you get the problem correct, then by all means take the extra 10 or 15 seconds, draw these pictures, make sure you get it right. I don't care if the person sitting next to you looks at your pictures and thinks that they look really, really stupid. Let them think that. You're going to get the answer right, and you're going to pass this exam, and you're going to get your CFA charter. They're not going to draw the pictures. They're going to think you look stupid, but they're not going to pass the exam. Who's going to look stupid then? Go ahead and draw pictures. Good way to make sure you pass this exam. Okay, some joint probabilities. The probability that both of two events will occur is called their joint probability. For example, the probability that interest rates will increase, we call that the probability of I, 40%. The probability that a recession occurs given that we have a rate increase, the probability of R given I, 70%. The joint probability, the probability that we both have a recession and an interest rate increase. Well, we already decided a couple of slides earlier that this is the probability of R given I times the probability of I. 0.7 times 0.4, 0.28. There's a 28% chance that we will have a recession and increased interest rates. That's the joint probability. Okay, here's that picture I was promising to you a little bit earlier. The probability of A or B. The formula that we had was that the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. If you look at the picture, this becomes very clear. The probability of A is that oval that's on the left side. The probability of A, that's figuring out the area on that whole oval. Notice the little football shape in the middle? Probability of A includes that little football. Probability of B, that's the one on the right. That's that whole oval on the right. We add that in there. Notice that we have added the football as part of that as well. So that little football in the middle, we've added that in there twice. We don't want to count it twice. So we've added it in twice. We have to subtract one off so that we only add it in once. That's why you subtract off the probability of A and B. If you can draw this picture, you will never make this mistake. You will always get the formula right. You will understand it perfectly. Okay, how can we use this addition rule? Well, let's get some information here. The probability of rising interest rates, 40%. The probability of a recession, 34%. The probability of both a recession and rising interest rates is 28%. We calculated that a few slides ago. We're using the same data. So what's the probability of either rising interest rates or recession? And remember, when we say this, this means either rising interest rates or recession or both. Both is okay. What do? We add up the probability of rising interest rates plus the probability of a recession, subtract off the probability of both. So we take our 40% plus our 34% minus our 28%, 46%. There's a 46% chance that we will have either a recession or rising interest rates or both. Now, if the events are mutually exclusive, of course, then the probability of A and B is 0. You can't have both mutually exclusive events happening. So the probability of both is going to be 0. The formula is a little bit simpler when you have mutually exclusive events because you're just subtracting off 0, so you can ignore that. If you want to memorize this formula, that's perfectly fine. I'm not sure that if I were taking this test, I would bother to memorize one more formula because I already know that the probability of A and B is equal to 0. And so if I had to do this calculation and at the end subtract 0, I think I'm okay with that, and I'd rather not have to burden my brain with one extra formula. But if this helps you visualize it and you got room in your brain to fit it in, by all means, memorize it. Okay, we talked earlier about independent events. If one of them occurs, that doesn't tell us anything about whether the other one occurs. If if that defines independent events, then obviously we can define dependent events where if one of them occurs, it does tell us something about whether the other one occurs. So far, the best example we have had of dependent events are events that are mutually exclusive. If we have two events that are mutually exclusive, tossing heads or tossing tails, those are dependent events because we know if we get heads, we don't get tails. So it changes the probability. If we get tails, we don't get heads. So knowing the outcome, will, whether it's heads or tails, will tell us about, knowing that it's heads will tell us about whether it's tails. Knowing that it's tails will tell us about whether it's heads. Okay? Independent events. If we have a coin and we toss it several times in a row, we generally assume that those tosses are independent. Whatever the probability is for getting heads the first toss is the same as the second, the third, the fifth, the 85th, the 167th, the 2000th, whatever. The probability of getting heads stays the same. And they're independent. So if we wanted to know the probability of getting 3 heads in a row, the multiplication rule says it's the probability of getting heads on the first try times the probability of getting heads on the second try times the probability of getting heads on the third try. If it's a fair coin, those are all 50%, 0.5 times 0.5 times 0.5, 0.125, or 12.5%. 1 chance out of 8 that you'll get 3 heads in a row with a fair coin. Now, unconditional probability. Suppose we have a bunch of data. We have the probability of an interest rate increase, 0.4. So we know that the probability of no interest rate increase, the probability of the complement, well, if it's 0.4 to get an interest rate increase, it's 0.6 that we get no interest rate increase. Suppose we know the probability of a recession given an increase, 0.7, the probability of a recession given no increase of 0.1. Remember from a couple of slides ago, we had that the probability of A can be broken down into the probability of A and B plus the probability of A and B complement. That's exactly what we're going to do here. So we take, here's the probability of R and I. This, I'll put a box around that. Let's change this to a square box. This is the probability of R and I. Let me write that above here. The probability of R and I. This one over here is the probability, there's my text box, is the probability of R and the complement of I. I can't do this as a superscript, so you're going to have to. Okay, so the probability of R and I plus the probability of R and I complement, that's from our slide 2 or 3 slides ago. 0.7 times 0.4 plus 0.1 times 0.6, 0.34. So we chopped up R into 2 different events. Recession with an increase, recession with no increase. Straightforward application. All right, this next slide shows you a probability tree. I would encourage you strongly to learn how to draw these trees and to use them. Drawing these trees will save you so much grief, will make it so much easier for you to pass this exam, make it so much easier for you to visualize what's going on. I strongly, strongly urge you to do this. So, here we have 2 possibilities. Either GDP is going to grow by more than 3% or it's not. It's going to grow by more than 3% or it's going to grow by 3% or less. 60% chance of the former, 40% chance of the latter. If GDP grows by more than 3%, then our stock might do well or our stock might do not so well. 30% chance that it does really well, 70% chance not so well. If GDP growth is less than or equal to 3%, then our stock might do well or might do poorly. If it does well, 60% chance of that. If it does poorly, 40% chance of that. And you can see what the earnings per share are for each of those outcomes. So high GDP growth, good stock performance, and EPS of $1.80. High GDP growth, fair to poor stock performance, EPS of $1.70. Low GDP growth, good stock performance, EPS of $1.30. Low GDP growth, poor stock performance, EPS of $1. We might, for example, be asked, what is the expected value of the earnings per share? Well, we take each of those possible outcomes there on the right, $1.80, $1.70, $1.30, $1, and we multiply each one of those by the probability that that situation occurs and add them up. That's just a straightforward expected value from the formula that we had a few slides ago for expected value. So 18% that we get $1.80, 42% that we get $1.70, 24% that we get $1.30, 16% that we get $1. Add up that weighted average, we get an expected earnings per share of $1.51. Expected value using total probability. Notice we had exactly that same formula. 18%, 0.18 times $1.80, 0.42 times $1.70, 0.24 times $1.30, 0.16 times $1. Now that's the unconditional. That's if we don't know anything. If we do know that GDP growth is greater than 3%. Oops, my mistake. If we do know that GDP growth is greater than 3%, then we only use the top part of that tree. We had if GDP growth is greater than 3%, there was a 30% chance of $1.80 per share and a 70% chance of $1.70 per share. Total of weighted average of $1.73. If GDP growth were less than or equal to 3%, we're in the bottom part of the tree. So then we use the bottom part, a 60% chance of $1.30 EPS, a 40% chance of a $1 EPS. That weighted average is $1.18. So you can see that drawing out these trees can make it much easier to do these calculations. It makes it very easy to visualize what's going on. Which branch of the tree do we need to use, and so on. Okay, a few more calculations, because I know you need a few more calculations. You're not quite happy until you have 87 different calculations you know how to do. Covariance, a measure of how two variables work together. Remember the variance that we had for a single variable, a single random variable. We would take each value for the variable, subtract the mean, square that, add that all up, divide by n. Now we're going, instead of having one variable, we're going to have two variables. So for this, we take each variable minus its mean. So x minus its mean times y minus its mean. Multiply those together, add those all up for all the possible values, divide by n. That gives us the covariance. The numbers can be positive, they can be negative, they can be zero, they can be big, they can be small. They could range from negative infinity all the way up to positive infinity. Notice that second bullet point there. It says units of covariance are difficult to interpret. The units of covariance will be the units on the x's times the units on the y's. So let's say, for example, that we have a baby giraffe. We're going to go back to the giraffes for a little while. We have a baby giraffe, and we're going to look at the height of that giraffe, and we're going to look at the value of the S&P 500. And suppose that the S&P 500 is generally going up, And to make it easy, let's value the S&P 500 in dollars. I know they don't usually put a dollar sign on it, but let's call it dollars. Well, the height of our baby giraffe is measured in, let's say, centimeters. Value of the S&P 500 is measured in dollars. The units of covariance will be centimeters times dollars. Not very easy to figure out exactly what the heck that means. So the units can be difficult to interpret. When we had variance, remember, the units were the square of the units of the underlying measurement. And because they were all squared, the variance never turned out to be negative. It was 0 or positive. So we could take the square root to get down to the standard deviation, which has the same units as the underlying measurements did. Here, we don't have that luxury, because we might have a negative number. We can't take the square root of a negative number. And we might have two different units. We might have centimeters, we might have dollars. So we can't take the square root of this. We have to find some other way of standardizing it. The thing to notice about covariance, look at that third bullet point. You will get a positive contribution to covariance when both numbers are above their average. So when the height of this baby giraffe is above its average, when the S&P 500 is above its average, you get a positive number times a positive number, positive contribution to the covariance. If they're both below their respective means, so the height of the giraffe is below its average, the S&P 500 is below its average, you get two negative numbers. Multiply two negative numbers together, you get a positive. That increases the covariance. The covariance will decrease if one of the numbers is above its average when the other one is below. So the baby giraffe height above its average when the S&P 500 is below its average, or the other way around. We can't standardize covariance, but we can't take the square root, as I said, to get down to something with the same units. So we have to figure out some other way to standardize it. And the way to do it is to try to just get rid of the units altogether. The way that we get rid of the units, remember that standard deviation of x is in the same units as the x's. Standard deviation of the y's is in the same units as the y's. So we take that covariance, which has the units of the x's times the units of the y's. We multiply those together, and we take the covariance, we divide by the two standard deviations. That gets rid of all of the units. We end up with a number we call correlation. So the correlation of two random variables, Ri and Rj, is the covariance of Ri and Rj divided by the standard deviation of Ri divided by the standard deviation of Rj. This is a standardized measure of the linear relationship between these two variables. So if we were to plot on a graph, if we were to plot Ri on the horizontal axis, Rj on the vertical axis, and then draw a best fit line through those data, if those points are very close to the line, then the correlation is going to be very close to either positive 1 or negative 1. It'll be close to positive 1 if the line slopes up, close to negative 1 if the line slopes down. If when we plot those dots and draw a best fit line through them, they just seem to be all over the place, not really close to the line at all, then the correlation is going to be close to 0. Again, for populations, we use Greek letters. We use the Greek letter rho down there on the bottom. Rho is the population correlation coefficient. R, we use English letters when we're talking about the correlation coefficient for a sample. Let me give you an example here. The covariance between two assets. Okay, let's stop right here. This is language that the finance people love to use, and it's very ambiguous. When we say the covariance between assets, what do we mean? What characteristic of these assets? are we measuring? Are we measuring the price? Are we measuring the returns? Are we measuring the output of these assets? Maybe it's oil and we're measuring output in barrels, and gold and we're measuring output in tons. There's nothing about this problem that tells us what characteristic we're measuring. So you have to understand finance people. When they use language like this, the covariance between two assets, almost always what they mean is the covariance between the returns of these two assets. They really should be explicit about it. They usually aren't. But that's what the language means. There's some other problems with this. I won't get into it. I could chew your ear off all day long on how bad their language is, but this is what they probably mean. So the covariance between the returns of asset A and asset B is 0.0046. The standard deviation of A's returns is 0.0623. The standard deviation of B's returns is 0.0091. What is the correlation between the returns on these two assets? Notice we're using rho, so we're using rho and we're using sigma, so we're obviously talking about populations of returns rather than just samples of returns. How do we do the calculation? We take the covariance, we divide by the standard deviation of A, standard deviation of B, 0.0046 divided by 0.0623 divided by 0.0991, correlation of 0.745, positive. So their returns tend to be above the average together and below the average together. Not all the time. If they were always that way, they'd have a row of +1. But pretty much every once in a while you might have one return above its average when the other one is below its average, but pretty good positive correlation. Now here we're going to do a calculation of expected value, variance, and standard deviation where we simply have a probability of particular outcomes. Fundamentally, this is exactly the same as what we've been doing on variance and standard deviation previously, but now instead of having a number of observations that we all treat the same, so we instead of having a number where we treat all of them the same, is what I meant to say, we have certain weights that we are applying to each one. We take the probability, we'll start off with expected value. We've done this calculation several times. You already know how to do this. The probability of recession is 25%, normal economy 50%, boom economy 25%. The return in a recession will be negative 10%, normal return 0.8%, return in a boom 22%. We take the probability of each one of these outcomes times its value, multiply those two together, add those up, we get an expected value of 7%. That one's straightforward. You've done that several times already. Let's move on to the next calculation. To get variance, we have to take the return and the expected value of the return, so the return minus the mean, square that, and multiply that by its probability. So in that first row for recession, we take a negative 10% return minus the mean of 7, so that gives us a negative 17%, square that, multiply that by 0.25, and that's what gives us the 0.00723. For the second one, we take the return of 0.08, 8%, minus the expected return, 7%. So 8% minus 7% is 1%. Square that, multiply that by the probability, 50%, that gives us 0.0005. Similarly for the third one, we add those all up, we get sigma squared, we get the variance 0.01290. Notice, and I want you to be very careful with this, notice in that last column, I will highlight this for you so that you can see this. Notice in this last column, we take the probability of that event, the probability of a recession, the probability of a normal economy, the probability of a boom economy, we multiply that probability times x minus mu squared. It's not the square of the probability. Some people do that occasionally. We square x minus mu, but we do not square the probability. Make sure that you remember that. Do not make that mistake. And obviously, if sigma squared is 0.01290, we take the square root of that, we get 0.1136, or 11.36%. All right, the expected return on a portfolio, the weighted average of the expected returns on the assets. This is exactly the same as the weighted average that we've covered several times before. I told you that it worked for actual returns, it works for expected returns. We've talked about it a few times here. It's going to show up again under portfolio management. This is an easy concept for you. You should be able to get this. By the time you're done studying this curriculum, you will have seen this explained to you 87 different times. You'll be able to get this one. This one's really easy. Now, the formula for the standard deviation of a portfolio. Once again, this is where finance people tend to be sloppy in their language. When we say the variance or the standard deviation of a portfolio, what we really mean is the variance of the portfolio's returns, or the standard deviation of the portfolio's returns. That's almost always what we're talking about. So make sure you understand that we're talking about returns here. The variance, kind of an ugly formula. The first term is the weight that asset A composes in our portfolio. So let's say asset A is 20% of our portfolio, asset B is 80%. So we take the weight of asset A squared, 20% times 20%, multiply that by the variance of asset A's returns, sigma squared of A. We take the weight of asset B, 80%, square that, weight squared, times the variance of B's returns, sigma squared of B. Then we add one extra term, 2 times the weight of asset A times the weight of asset B, so 2 times 0.2 times 0.8 times the covariance of A and B, the covariance of A and B's returns. And remember, if you take the formula for the correlation coefficient of A's and B's returns, solve it for covariance, you get what you see in the note down here. So let me highlight this. This comes straight from the definition of the correlation coefficient, just solving for covariance. Now, I want you to take a look at that last formula down there. Notice that sigma squared of A is positive. W squared of A is positive. Sigma squared of B is positive, and W squared of B is positive. So those first two terms are all positive numbers. Those are all going to make the variance increase. The only possible way that you could make the variance of the portfolio returns go down is by making that last term decrease. Well, in that last term, 2 is positive, the weight of A is positive, the weight of B is positive. We'll assume you're not short selling here, so those two weights are positive. Sigma of A is positive, sigma of B is positive. So the only way that you're going to get this number, this variance for the portfolio's returns to decrease is by lowering the value of rho. This gives us a fundamental idea of portfolio diversification, that if you want to lower the volatility of your portfolio's returns, the way that you do it is by finding assets whose individual returns, as we take pairs of assets, asset A and B, asset B and C, asset A and C, and so on, if the correlation of their returns is low, the lower that number, the smaller that row, the lower the variance of our portfolio's returns. So a fundamental idea of diversification, we'll see this again under portfolio management, is that low correlations of returns leads to lower volatility of the portfolio's returns. Very important concept. Okay, now we have a joint probability function. We have a 15% probability that RA is 20% and RB is 40%. We have a 60% probability that RA is 15% and RB is 20%. We have a 25% probability that RA is 4% and RB is 0%. Notice, 60% plus 15% plus 25% adds up to 1. So each of these other boxes, there are 6 other boxes in this table, those all have probabilities of 0 because we can only go up to 100%. So those all have probabilities of 0. How are we going to calculate the covariance? We take each of those probabilities, we multiply the probability times exactly what you normally do for covariance. The value of RA minus its mean times the value of RB minus its mean. So 20 minus 0.13 times 40 minus 0.18. Each time we use the value for A minus the mean of A and the value for B minus the mean of B. Multiply that by its probability. Do the same for the other 3. Add them all up. 0.0066. If we calculate the standard deviation of A's returns and the standard deviation of B's returns, we can use those along with this covariance to get the correlation of A's and B's returns. All right, Bayes' formula. I promised you this from a long time ago. Bayes' formula. An easy way to do the Bayes' formula calculations is to set up a tree. This is just like the tree that we had before, where we had the probability of recession given an interest rate hike, or probability of a recession given no interest rate hike, and so on. Exactly the same kind of tree, exactly the same kind of calculations. 60% probability of an interest rate cut. If that happens, a 70% probability of good earnings and 30% probability of poor earnings. So the probability of good earnings and an interest rate cut, 42%. Probability of poor earnings and an interest rate cut, 18%. Probability of good earnings with no interest rate cut, 8%. Probability of poor earnings with an interest rate cut, 32%. Suppose somebody asked you, what's the probability of good earnings? Well, you simply go to the end of the tree and you circle all the probabilities that go with good earnings. There are 2 of them. We could have good earnings and an interest rate cut, good earnings and no interest rate cut. Does this sound familiar? Yes, this is just dividing up the probability of A into A and B and A and not B. We saw this a few slides ago. Exactly the same kind of calculation. What's the probability of good earnings? Let's see, good earnings given, no, I'm sorry, what's the probability, I'm reading this backwards, what's the probability that we had an interest rate cut given that we had good earnings? Well, that's 42%, this number up here on the top, divided by the total of those 2, 42 plus 8. 42 over 50, 84%. The way that Bayes' theorem works is we already know the probability of G given C. The probability of G given C is this 70% here. we're going to use that to calculate the probability of C given G. Okay, the last few ideas. Factorial for labeling. Suppose you have 10 stocks. 5 are going to be rated buy, 3 are going to be rated hold, 2 are going to be rated sell. How many ways are there to do this? Frankly, if you ask me, this is a silly question. Yes, I know the idea is to try to test you on counting these things, but the problem is that this question makes it sound as if you are going to rate them as buy, hold, and sell arbitrarily, and any one of those is as good as any other. And that, of course, is ridiculous. You rate it as a buy because you did analysis and you think you should buy it. You rate it as a sell because you did analysis and you think you should sell it. So the premise of the question is kind of silly, but it's a chance to give you, to let you work on a calculation, and CFA Institute will do this kind of thing. Here you go. It's 10 factorial in the numerator. We have 10 stocks, so we take 10 factorial. That means 1 times 2 times 3 times 4 all the way up to 10. That's what that means. In the denominator, we have numbers for each of the different kinds of labels we have. 5 buys, 3 holds, 2 sells, and factorials for each of those. So if this 5 factorial is 1 times 2 times 3 times 4 times 5, 3 factorial is 1 times 2 times 3, and so on. We do that calculation 2,520 ways that we can have 5 stocks rated a buy, 3 stocks rated a hold, and 2 stocks rated a sell. And by the way, out of those 2,520, there's probably only one labeling that's correct, that if you did your analysis, there's only one way of labeling these that's correct. So maybe the idea is that we want to know what's the probability that this company got it right. It would be 1 out of 2,500, 1 out of 2,520. When order doesn't matter, in the previous example, order didn't matter. It didn't matter whether you had stock A as a buy and then stock B as a hold, or first stock B as a hold and then later stock A as a buy. The order doesn't matter. It doesn't matter which one you label first. What matters is which label they get. In this case, we use what's called the formula for combinations. Combinations means order doesn't matter. You have 5 stocks and you want to play orders, and you want to place orders to sell 3 of them. How many different combinations are there? Well, it doesn't matter whether you place the sell order first on A, then on B, then on C, or first on C, and then on B, and then on A. They're all the same. So the order doesn't matter. And the way that you read this symbol that we have here, the little n, and then this capital C, and then the little r, this is read the number of ways of choosing n objects r at a time. So in this case, it's the number of ways of choosing 5 stocks 3 at a time. We start with 5. We want to choose 3 out of those 5. And the formula is you take the 5 in the numerator, 5 factorial, so 1 times 2 times 3 times 4 times 5. In the denominator, you have 3 factorial. Those are the 3 stocks we want to place sell orders, 1 times 2 times 3. And you take 2 factorial. That's 5 minus 3 factorial, 1 times 2. So you do the calculation. 1 times 2 times 3 times 4 times 5 in the numerator, 1 times 2, and 1 times 2 times 3 in the denominator. Do all the multiplication and the division. You come up with 10 ways that you can do this. Again, I think CFA Institute wants to test you on this, but this might not be the most realistic example for doing that, because you're not arbitrarily going to pick 3 stocks to sell. Presumably you're going to do analysis and pick the 3 worst stocks to sell and keep the 2 good ones. What if the order does matter? So you don't just want to pick 3 stocks to sell, but you want to decide which one goes first, which one goes second, which one goes third. In that case, you use the permutation formula. This formula here, this symbol, is read the number of ways to permute in objects r at a time. So we have 5 objects. We want to permute 3 at a time. We want to pick 3, but then we want to check to see how many different ways we can do those 3. So the order does matter. Notice that for the combinations, we had an extra r factorial down here in the denominator. Now we don't have that r factorial. We have n factorial in the numerator, n minus r factorial in the denominator. If you have 5 stocks, you want to sell 3 one at a time. The order of the stocks matters. How many different ways can you do it? 5 factorial over 2 factorial gives us 60 ways of doing it. On your TI calculator, the nice thing is that it does have buttons to do combinations and permutations. So for combinations, you put in the first number, n, the number of stocks you have, then you press second, and then you press the NCR button, which when I look at my calculator here, I'm scanning, and the NCR is above the plus sign. So you hit the second and then the plus button, and that gives you the number of combinations. Then you hit 3, that's how many you're going to take at each time. Hit the equal sign, you get 10. If the order matters, and so we want to do permutations, then you press the first number, 5, that's how many stocks we have. The second button and the minus, that gives you the permutations. Then you press how many we're going to do at a time, 3, press enter, and you get 60. So there you go. Shortcuts for doing it on the TI calculator. Unfortunately, if you have the HP calculator, it does not have built-in functions for combinations and permutations. You're going to have to do the factorials yourself. If you do that, be sure, write out what those factorials are, cancel out as many terms as you can before doing the calculation. Otherwise, you may end up with really, really huge numbers and a lot of waste of time when you do the calculations. And that about wraps it up.